I'm a little late today. I picked up a cold from someone. I don't know who was. Isaac, is it you? You gave it to me. Jacob, are you here today, Jacob? No, Jacob. Let me get it now. All right, we'll go to the other one. Mark, I'm back in the system here. Yeah, back in the groove. Come on, Mara. You get called a lot. I don't think this thing is very good. I don't think it's random. It is warm in here today. All right. So review session tonight. How many people are going to come to that tonight? We get a feel for like how much pizza to get. Yeah, bring a pizza. It's a party. It's a party. Okay. All right. So there's a lot of you. All right. I'll get some pizza. How many are going to wear a costume? Hell yeah. Ed, are you coming as Ed? Ed, are you coming as Ed Sheeran?
No.
Just grab a guitar and you're ready, dude.
Dad would have a guitar and I'll do it.
Only if you sing us a song. I'll find you a guitar if you sing to us. All right. I'll be there. I'll have some pizza. Well, like I said, I was a little skeptical last year. I was like, oh, these are college kids. They don't want to do that. But everybody showed up and did it. It was awesome. I had fun. Isaac, you going to do it?
He's going to Snow White.
I can see that. I can see it. All right. So exam on Friday, I posted those 2 example problems. That's what we're going to go over tonight. And then and it's going to be on kinematics and F equals MA. Your last 3 homeworks, I think, is what it'll be on. Or 2. I don't remember if we did a couple problems the week of an exam or not. So that's that. Right now we're working on work energy. Kind of some key concepts here, right? Same equation that we had before, right? This same equation. It's just now we pick up some extra parts. We pick up kinetic energy associated with the body rotating. There is energy associated with this, and it's just Ig omega squared, right? Very analogous. Translation is just 1/2 mv squared. Rotation is 1/2 I omega squared, right? Then we went on with couples, and we said, yep, forces, we still have these kind of forces. Forces acting over distances do work. Moments acting over rotations do work, okay? We're going to see one of those today. And then when we get to springs, we have 1/2 Ks squared is the energy associated with linear springs. And then the springs that we have down below here, torsional springs, the energy associated with those is 1/2 K theta squared. So just very analogous, same procedure that we used before. The equations are very similar. And we'll see today, though, the things get a little more complicated. Is we have to do some kinematics and stuff to kind of square this all up. There's just more going on, but same process. All right, so we worked on this problem right here. It starts out. It was starting out over here at state 1, and it was rolling over to state 2, right? And so this thing was stretched originally. I think it's still stretched a little bit on this end over here. And they give us some things here. And we're asked to find omega over here at state 2, okay? And I think it's starting out at rest. Yeah, released from rest. And so all we've gotten so far when we started working this thing out is we did a free body diagram, right? We have mass times gravity going down, normal force going up, a little friction force there, and a spring force there. And we started talking about this, the spring. It's going to do work, but we're putting that in the potential energy term. Mg won't do work because there's no change in height, and even if it was changing in height, we would put it in the potential energy term. Normal force never does work. Friction force will do work, but in this case, since it's not sliding, it doesn't do work, right? All it's there to do is get this thing to start rolling. That's it. And so we just made this little, a couple ways to look at it. The point that it acts on, it keeps changing, right? As this thing rolls around, that point changes. And so it's not acting on one single point for more than an instant, okay? And then, or just remember that if the only thing the friction is doing is getting the wheel to roll, it doesn't do work. So in this case, we don't have any work that's being done. Okay, so that's our free body diagram. We're ready there. All right. I'm gonna get my notes here. All right, now we're ready to write down the energy equation, right? So step 2 here. Okay. Energy equation, just write it out every time. Every time. Even if you know some of the terms are going to go to 0, I always write the whole thing out. T1 plus V1 plus work done 1 to 2 is equal to T2 plus V2. Is it warm in here? It's comfortable. I'm sweating up here. You guys mind if I lecture with my shirt off? Wouldn't that be a sight? Somebody walks by out here, like MSU Fridays walks by, and then I'm in here with my shirt off. I'm sweating. All right. Maybe I got a fever. Maybe I'm feverish. I don't know. All right, so then we look at this, right? And we look at here and say, all right, are any of these terms equal to 0, right? And one of the we just got done saying that this was 0, right? There's no external forces doing work in this case, so I'm going to say that sucker's equal to 0. Okay. Kinetic energy at the beginning, that's 0, right? It was told that it was starting out at rest, so that guy's 0. Right. I always like to do it right here before I expand it out and then start crossing stuff out, but it's okay, you can cross stuff out later. But right now I noticed that everything's 0. Okay, now we're ready to expand here. Expand and simplify, right? So we can start writing down some of these terms. The potential energy at the beginning. Like I said, I didn't go through all these terms. Is there potential energy at the beginning? There is, because this spring is stretched, right? It's right now, it's stretched out to 5 feet, and its original length is 1 foot, so it has a stretch of 4 feet. So there's potential energy at the beginning. Over here on state 2, there's potential energy because at state 2, it's 4 feet. It's 4 feet long. Okay, and so then its unstretched length is 1, so it's going to be stretched over here too. So there's potential energy. That's why we have potential energy at state 2, and then we're after the kinetic energy at state 2. Right, we're after that. So that's why all those terms are at. Okay, so now we just go back and expand. So the only potential energy we have at the beginning is in that spring. So we expand to that. Be 1/2 K S1 squared. That's it. That's everything at the beginning. Then I look at the kinetic energy at state 2. That's going to be equal to 1/2 mVg squared. That's the translation part of the wheel, right? But then it also has a rotational part. 1/2 Ig omega squared, right? That's all the kinetic energy at state 2. You have to have both components. You have to have the translation and the rotation. That's an extra component that we haven't had before. Okay? And then we have to add on to it the potential energy, which is 1/2 K S2 squared. If you want to highlight those, right? This is V1. Both of these terms are T2. And this is V2. Okay. All right, so that's the only equation I got. That's the only one I got. I got to do some kinematics, right? I got to determine what S1 is. We already briefly talked about that. I need to determine what S1 is. I need to figure out what S2 is. I would consider that kinematics. So it's the geometry of motion. But then I still have 2 left. I got VG and omega, right? I got 2 unknowns there. And I need to get it down to 1 unknown because this is the only equation I get. And that's where our kinematics come in. I have to relate the velocity of the center to the omega. I have to relate both of those things, right? And that's where our kinematics comes in. All right, so let's do that. Kinematics. All right, so let's do the stretching first. That's an easy one. Right. S1 is going to be, it's stretched out to 5 feet, right? And its unstretched length is 1 foot. And so S1 is equal to 4 feet. S2, very similarly, it was stretched out to 4 feet at state 2. It's 1 foot long. That'll be 3 feet. Right, so now I know what S1 and S2 are. Those are two unknowns up above that I need to fill in. Okay, now we got to do the kinematics. And so, right, there's a couple ways to do this, right? You got to go back to, I'll do it the long way, but then we'll all just point out that this is just a rolling wheel, and we kind of already have that. But, right, I do know the velocity right here is 0, right? And I want to know the velocity at the mass center. That's what I need to do. So I'm going to take a step from here up to there, right? And determine what that relationship is. VB is equal to, we'll call VA, that'll be the base, plus omega crossed with R, G is seen from A. This guy's 0. Right at the base of the wheel is 0. Omega in the K crossed with 0.75 in the J. Right, that's just the radius of that wheel. And this you would get negative 0.75 omega in the I direction. And that relates, right, the velocity of the center. I guess we'll call that VG, I guess is what we're calling that VB. Right. The variable I'm using is VG. And VA would be just this part right here. Just that bottom point right there. And so if you don't see it, that it's a rolling wheel, and you don't recognize that we have rolling wheel kinematics already, you just do that. You would just stick to our plan of like doing our kinematics, starting at a point that we know something about and step into a point that we want to know something about. But that's that relationship. We're just missing that relationship between what the mass center is doing and what omega is doing, because I need that up above, right? I need that up above, right? Or, like I said, right? Or we had this before. VG was just equal to negative R omega. That was rolling wheel kinematics. My pencil just vibrated, I don't know why. But that's just rolling wheel, that's rolling wheel kinematics. And like I said, if you look back at our notes, we had that. I would do that when you make your note sheet. That's one of the things I would put in there. It's just rolling wheel kinematics. That's just omega's this way, right? And so VG would be going to the left. That's where that comes from. So you can put an or, just kind of a shortcut. Or rolling wheel. Or rolling wheel kinematics. All right, that's our missing relationship. Okay, and so the last step is just going to be solving it. Okay, I'll copy this down so we can see what we're doing here. So let's fill in all of our knowns here. 1/2. Our K is given to us as 2. Our stretch is 4, we determined before. It's equal to 1/2. You could be careful of your masses, right? So it's 30 pounds. So we got to put that into slugs, right? So that's why, and you have to do that, so make sure you do that. You can't just put it in the pounds there. 30 over 32.2. That times VG, which is negative 0.75 omega squared. That's my VG term, plus 1/2 IG omega squared. Oh, I know what IG is. Do I know what IG is? Did I ever determine what IG was?
It's given.
It's given. So let me just erase that. That is given as 0.335 omega squared plus 1/2. My K is 2. My stretch now is 3 squared. There she is, right? Everything's, you got my one equation, I got it down to one unknown, and the one unknown is omega, and I solve for omega. Plug that in my calculator. Doody-doop. Equal plus or minus 4.04 rads per second. Right, and you could determine which one. Actually, in this case, one answer is correct, and that would be the positive. Right, it's gonna be rolling that way to the left, and so it would be a positive omega would be my right answer. Either one works in terms of the energy balance, but then you'd have to apply a little bit of kinematics knowledge there, because right, it's gonna be rolling that way. It's not gonna be rolling back that way. Sometimes the positive negative makes sense, like those if I'm either spinning it this way in the air or backwards in the air, it doesn't matter. In this case, there's only one real right answer. Cool. So they're not bad, right? They're the same process. The only thing that gets a little more difficult is these kinematics. We'll do one in a few minutes that the kinematics gets really, pretty difficult, very integral to the problem. All right, let's go on to the next one. Well, not too bad, right? Starting up here at the top, rolling down. Again, this is gonna be rolling wheel kinematics, rolling down a certain distance. Mass is 5 kilograms. The radius is 0.2 meters. The angle, this angle right here is 15 degrees. The disc is stationary, at a constant, it's stationary. And then there's a moment that's gonna be applied, a constant moment that's gonna be applied of 10 Newton meters. And then it starts rolling down the hill just due to gravity, right? And then what is the velocity of the mass center of the disk when it is moved a distance of 0.4? So when this distance here is traveled 0.4 meters, okay? That's what we're supposed to do, right? So then you look at this, you're like, oh, what do I do? Well, you just stick to the plan, right? Again, when we first start learning these, I always do a free body diagram. And since you're just learning these, I would do the free body diagram to see everything that's acting on it. I like to do my body in black. Oh, I can't even draw a circle with the help of a circle. With the help of the iPad, I mean. Nailed it. First try. It's aggressively big. Okay. All right, and it's sitting on a slope. I'll try to get the slope. Okay. All right, force is acting on it. Unders. There we go. What are we gonna do when you're not around sometime, right? Better always be here. I'll always notice if you're not here, right? Mass times gravity. What else we got? Normal force, yep. Normal force, perpendicular to the surface here, right? Normal force, friction force. What else? Yeah, the moment, the applied moment. I would put legs on my moment, just so. Because we also have another M floating around the mass, right? That's it, right? That should be everything that's on there. That should be everything we got. Okay? And so then again, what I'm doing is I'm looking to see what does work, right? What does work? Friction force, all it's doing is making the wheel roll. In this case, there's no sliding happening, so the friction force is not going to do work. Normal force never does work. Mass times gravity, in this case, will do work, but we're putting in the potential energy term. And that moment right there, that moment's going to do work. That's an external force. Right? That's an external moment or external force that's going to do work. So we are going to have a U term in our equations down below. All right, so we've identified that. 2. Equation. Write down my equation. T1. T1 plus V1 plus work done 1 to 2 is equal to T2 plus V2. Okay. Thing is starting at rest, so no kinetic energy at the beginning. Right? Do we have potential energy at the beginning? Yep. Right? Well, it depends on how I define my datum. I like to define my datum as being 0 at the bottom. So in this case, I will say, yeah, I'll have potential energy at the top. Okay? We'll define the datum a little bit later when we do kinematics. Work being done from 1 to 2, just said that we're going to have that term, right? We're after the kinetic energy at state 2. We're after how fast is it going at state 2. And then potential energy at state 2. I'm going to say that sucker's 0 because, again, I'm going to define my datum to be 0 at the bottom. Right. That's up to me. I could make it, I could flip it around if I wanted to. I could have negative potential energy at the bottom if I wanted. Expand. Is it the sound of steam being injected into this room? Like we're in a sauna right now. Okay. So potential energy at the beginning. mgy1, right? Because like I said, I like to make myself have potential energy at the top. So that's the potential energy from the change in height at the top, plus that's it, right? That's the only potential energy I have at the beginning. And then we're gonna have the work being done. Right? Put my legs on my moment. That's gonna be m times theta is equal to 1/2 is the kinetic energy at state 2, 1/2 mvg squared plus 1/2 ig omega squared. You have to have both of those components in there, right? There's no fixed point. Later on, we're going to do one that has a fixed point, and you can get rid of the VG squared term when we have a fixed point. But when there isn't a fixed point, I have to account for the energy associated with the mass center translating. That's what this is, and then also the energy associated with the wheel rolling, which is the Ig omega squared, right? So you see some kinematics I have to do. I have to determine what y1 is. I need to figure out what theta is. I need to figure out how Vg and omega relate to each other, right? I can do all of those. So those, I would say all that's kinematics. This is the only equation I got, right? And right now I have 4 unknowns. I got to get down to 1. 4. Got to do some kinematics, right? So this thing is going to go down. It's going down 0.4, right? And so I need to figure, this guy's going 0.4. I need to find this change in height. That change in height right there. 0.4. Right? And then that angle right there, that'll be my beta right there. It's 15. If that's what it is. Y1 is just going to be equal to 0.4 times sine of 15. 0.1 meters. Right, because these equations are all based on what the mass center is doing. Where's my mass center height change? My mass center height change is right there. Right, 0.4 times that sine of beta, which is 15 degrees, which gives me this right here. So this would be 0.1. Right, so again, based all on what the mass center is doing. That y does. All right, keep going. I'm going to use my rolling wheel kinematics. We just derived this before several times now. Vg is just equal to negative r omega. Right, that comes from rolling wheel. Little shortcut. You didn't have to notice that shortcut. You could do, if you didn't notice that, you just step from one point to the other, to another point. Okay. B, how far does it, right? So the other thing you could do is say B is equal to negative r times theta. This is also, if you look back at a rolling wheel kinematics, that relationship also comes from the same thing, from rolling wheel, right? If I want to determine how far something moves when it rolls a certain radius, it's just that r times that theta. Right? And another way to look at it, I mean, if velocity is just r times omega, distance is just going to be r times theta. A couple different ways to look at it, but that's where that comes from here. Okay. So then you go like this. I know B, right? B is 0.4. Equal 0.4. And so then I could say theta is equal to negative 0.4 over r. In this case, that's equal to negative 0.4 over 0.2. Okay, so that's what the theta is. Because I need the theta, right? Because that's the distance that moment is working across. Okay, so now we come down where we got all the missing components. So I'm going to take this too, just to bring it down. Step 5 is solving. Let's just expand this thing out. Oh, I didn't want that. I wanted to copy the other one, sorry. I wanted to copy this one. All right, so plug in all of our knowns here. Mass is 5, gravity is 9.81 in this case. Y1 is 0.1, we just found that. Plus, you gotta be, we think about this now. We're getting to this m times theta term, right? We gotta think about the signs of it. What is the sign of this moment that's applied? It's a negative, right? Is it a negative? It's a negative, right? Roll my fingers that way. Thumb going into the screen, right? If it's that way, it comes out that way, right? It goes that way, right? So that's a negative. So we can do that. We could say that. So if you're keeping track of the signs, that should be a negative 10, right? My theta that I just determined, right? That's a negative theta, negative 0.4 over 0.2. Watch this. I'm gonna do that math in my head. Negative 0.2. It's 2, motherfuckers. It's 2. Goddamn, that's what happens when it happens when I try to do it in my head. This is why I use my calculator. You see why I use my calculator. It's like that. I do it. In my defense, I do that didn't look right. I wasn't finished. I was gonna be 0.2 divided by 0.2 times 2. That's what I was gonna do. It's 2. God damn it. Right, so the point that I was trying to, 1, I don't know how to do math. 2, those 2 negatives make a positive, right? Those 2 negatives make a positive. So I could be really careful. There's a couple different ways to do it. I could be really careful with my signs. I had to be careful with my signs up here and make sure that I knew that was a negative theta as it was rolling, right? And so I knew that was negative. I was careful that moment was a negative moment when it went in here. Those 2 negatives make a positive. Or, right, we made this comment before with forces. If the forces act in the direction of motion, it does positive work. If the forces act in the opposite direction of motion, then it does negative work. So in this case, that moment is acting in the direction of motion, right? It's adding energy to the system as opposed to taking energy out of the system, right? It's speeding things up. And so there's a couple different ways to do that. You can get careful of your signs like I did in the problem, or I can just look at it and say, well, I know that moment acting over that theta is going to be doing positive work because it's acting in the direction of the theta. And so I know that this term right here, when I get here, this has to be positive, right? So just either way you could do it, right? I usually do it just ad hoc, and I look at it and say, all right, is that positive? Is it acting in the direction of motion that it's doing positive work? Is it acting opposite direction of motion that's doing negative work? Or be careful with your signs. We could say that. Let's do that. Of signs. Or know that forces and moments. Where'd it go? Acting in direction of motion do positive work. Yeah. I used to do that. And opposite of motion. Okay, so just a cautionary tale as you're going through there, right? And we keep, like I said, that's it. That ends up being correct the way we did our signs there. All right, and that's equal to 1/2. Mass is 5. VG, we have a relationship. My VG is 0.2 omega squared plus 1/2 IG omega squared. In this case, they didn't give me IG, so I'd have to calculate it. If you look it up, this is just 1/2 MR squared. .2 is what that ends up being. They didn't give us IG, but you'd have to look it up, a disc, a rolling disc, and if you substitute all that, it ends up being 0.2. So there it is, right? Everything related to omega, right? They didn't ask us for omega, they asked us for the velocity of the mass center, but I have a relationship for that later. So anyways, I go through, I solve for omega, that ends up being plus or minus 13. And then VG is just going to be negative R times omega. It's going to be equal to plus or minus 2.6 meters per. Sorry, my plus or minus messed up. Plus or minus 2.6 meters per second. Right? And then again, we know that it's going to be the plus. It's going to be the plus. 2.6 meters per second, right? Because it's going to be rolling to the right. Okay, so we had to, like I said, a lot of the problem, you lose your signs, right? You lose your signs as you're going through this because of this, of the velocities in particular, right? Because you're squaring them. Those two signs are squared, and so then when it comes out, it ends up being plus or minus. So you have to use a little bit of logic there to figure out which one it is. Cool. All right. Right. Hopefully you see these ain't so bad. All right, let's do this guy, and then we'll get to this one. And you're like, oh shit. All right. We have three different bodies floating around. Right. We got this guy, we got this bar right here, and we got the disc. We have all three of those things, right? And so all three have components associated with it, especially when we're talking energy associated with these, right? We got translational energy of this guy, we have translation and rotation of this guy, and we have rotation and translation of this guy. So when we get to the kinetic energy term, we're gonna have three of those floating around. Okay, let's do it. We'll get through part of this before we go. All right. So it starts out this state right here as you see it, and then it asks for the velocity and omegas and stuff like that of it at state 2, and state 2 is going to be when this thing's down here like this. Oh, I could do better than that. Now let me make that go all the way through here. Okay, so that's it, state 2. So it's starting out there and it's going down until it's flat right there. Okay, and we're said to solve this problem. So let's do the free body diagrams here to start things out. We're looking for forces doing work. And we actually get 3 free body diagrams, one for each of our objects. There's mass A. Right. I'm gonna save you some work here. Anders, mass times gravity. Stole your thunder. Some normal force, right? We don't know which direction it's acting. It could be on either side, right? It could be this side too, or maybe it could be both sides at some point. Right? Doesn't matter. It's stuck in there, right? Then you're gonna have that bars coming up. F bar 1. Right, that's it. The bar's pushing on it. Mass times gravity is acting down. There'll be a normal force. Oh, I didn't label it. Right? It'll be a normal force. You know, in some cases it might be acting one way. Some cases it might be acting the other way. But it's not. There's no motion in that direction. There's holding it in place. Okay? That's our first object. Next one is the bar. Right? Equal and opposite here. We're going to have F bar 1 down here. This doesn't have to be 2 force, but we don't know if these are the same or not, but it doesn't matter. F bar 2. And then you're going to have mass times gravity that's going to act right at the mass center. All right, be careful. There's different masses floating around, right? The mass of the bar times gravity. This one over here should be mass of A times gravity. Okay, and the last object is that disc over there. And again, we're going to have mass times gravity of this. This is mass B times gravity. Equal and opposite, this F bar 2. Acting right there. We'll have a normal force acting here. Friction force acting here. Okay, that should be everything, right? Again, we're looking for forces doing work. Right? Normal forces never do work, so these guys aren't going to do work. Mass times gravity, it's going to do work. And there is a change in height, but we're not doing that. We're putting it in the potential energy term instead. Right? This F bar, right? We made a conjecture, I guess, before that said if there's internal force pairs, they cancel each other out. And so in this guy, right, this F bar over here, it's going to do work. This F bar is going to do work on this object, right? But then that same F bar it's equal and opposite is going to do work on the bar at the same time. But since one's acting in the direction of motion and one's acting in the opposite direction of motion, they cancel each other out. So this guy and this guy cancel it. They're internal force pairs. They cancel each other out. Yeah?
Why doesn't F bar act parallel through the bar?
Because... There we go. Good. It's not necessarily a 2-force element, right? In trusses, we say that is the case, but things are moving. So I don't know. Arbitrary. Yeah. And all I'm using them for right now is, like, I have drawn them as 2-force, is just like this, but there's not necessarily, because it is rotating. Yeah. Right? So if it wasn't rotating, like in statics, it's not rotating, it's just like perfect, right? And everything's just, nothing's moving, and then it goes right through the center, and that's an assumption we made. But there has to be, since it is rotating, it can't be like that, right? Those forces have to be not equal to each other, not straight down the axes, because then something has to make that bar rotate, and that imbalance is there. So I just kind of drew them arbitrary, because I don't know, and it doesn't matter. The only reason I put them there was to say that one's acting over distance in the direction of motion, the other one's acting over a distance in the opposite direction of motion. They're internal force pairs that cancel each other out. Okay.
The only thing we know is that they aren't acting.
Yes. Yep. We could say that internal force pairs do work. Okay. Mass times gravity, again, does work, but we're not putting in the work term. This F bar and this F bar, again, cancel each other out. This guy, right, and we're going to put the potential energy term, and there's no change in height of that guy. Friction force is only making the wheel roll. Normal force doesn't do anything. All right, the other thing to tell yourself, now that we've done this more, if they don't put, for these problems that we're dealing with, if they don't put friction in there, right, friction and sliding isn't happening, okay, then we know that's, or if they don't put an external moment or they don't put an external force, then there's no work, right? And it's just, now we've done this enough, just look for that, right? Is there an external component here? No, they didn't, you know, if they came in and said, oh, I'm gonna put a big old F right there. Now there's an external force being applied, right? Or in like your homework, they had a hand, right? There was an actual hand there, and that hand was the external work thing doing work, right?
Maybe I missed this, but for FR2, is that going to do the same thing on the wheel that it did on the block where those two end up canceling?
Yes. Yep. Exactly. Yep. I skipped over that. They're both internal force pairs.
Okay.
Yep. Right. I mean, if you really get crazy about it, you know, again, there's these things everywhere, right? Like if I come in and right, you're learning about free, you know, where you do like little. Where you cut your beam in different locations, stuff. Really, if I cut this beam, then there's going to be, you know, equal and opposite forces inside of there. So inside of it, there's always these internal force pairs. And then the reason we highlight them here is because you're going from one object to another object. And so, and when you're drawing your free body diagrams, they show up. But there's just, they all fall underneath this. Internal force pairs don't do work. Yep, good question. Okay. All right, we'll call it there. You guys have an exam, right?
Yeah, I do.
Nice. You guys are excited about that.